Well, now in this second part of the chapter 2, we are going to address the last topic of the rotation of diatomic molecules, and specifically the model of the non-rigid rotator, which is actually closer to the reality of things, and sometimes it's called the real rotator. Basically, to move from the rigid rotator, which is the first approximation that we have seen in the first video, and go to the non-rigid rotator, there is a small correction which is called the correction of the centrifugal or centrifuge distortion. So let me start with explaining what this is going to be about. Well, as we have seen in the first video, basically we're talking about a diatomic molecule, two different atoms, so it's a heteronuclei molecule which is rotating around the axis going through the center of mass. Now, what we have said before in the rigid rotator, so let me write it down, in the rigid rotator approximation or model, which is an approximation, well, basically the distance, this distance here, is unchangeable. So this distance, R0, the interatomic distance, is constant and does not change with omega. Okay, so this is considered constant. So even if the rotational speed or the energy or omega increases, well, R0 remains unchangeable, remains constant. Now, what does that mean? That means that if R0 remains constant, so if the distance between the atoms remains constant, then I, the momentum of inertia, which is equal to mu r squared, or in this case R0 squared, also remains constant. However, this is not real, because basically, imagine that you take a big platter like this. Let's see if I can draw that. Well, not really. Let me put it differently then, maybe like this. Okay. And this is from the inside. Okay. Imagine now that you take a ball and you put it in the middle. Let's call this a ball, let's say just. And then you start shaking or rotating this one like this. So you take it with your hands and you start rotating it. What happens, this one will start rotate, the ball itself. And the more your rotational speed here of the entire platter will increase, well, you will see that this one will start doing motion like this, and then like this, and then at the end of the day, the ball will start actually turning around the sides of the platter, right? It's as if it's trying to get out of it. So if you increase your speed even more, then this pop ball will just go out. And you can try this experience. But the question is, what makes the ball turn around and go to the sides of the platter and even go out? Well, when when the rotational speed or angular velocity increases, the ball inside the platter will experience a force that pushes it away from the center. This is called the centrifugal force. Okay? So the centrifugal force results from the angular velocity. The more the angular velocity is high, the more the centrifugal force is high. Another example that you also know, two examples actually. Well, imagine a guy holding a bucket full of water. This is a bucket, and the bucket is filled with water inside. Just let me draw that. It's going to be like this, okay? And this bucket has the water inside, and then this guy starts rotating actually the bucket around in a rotational movement with a certain speed. Well, when this bucket arrives here, well, with his hand that becomes suddenly very long, okay, he must be holding it, otherwise it will fall down, okay. Well, he will notice that the water remains at the end. It does not fall down. So the water, write it down, the water does not fall down. And why it does not fall down? Well, basically because although there is the weight, this is the weight of the water, so the gravitational force, but in fact there is another force that pushes it back, and that's the centrifugal force, or centrifugal force. Well, this force maintains, because of the rotation, the water inside the bucket. Now, if there is no rotation, so if the guy just simply holds the bucket of water on top of his head, he will get wet, because the water will just fall down under the effect of its weight. Now, this is a centrifugal force. Well, we are in a similar situation. Here, we are in a similar situation. Why? Because basically, let me go back and take this one. No. Okay. Well, basically, because we have this first mass of the first atom, and we have the second atom forming the molecule, right? And what happens is, if it was not rotating, the distance between the two is r0, right? Now, the more it rotates faster, if this is r0, it's too big, r0, and it's rotating around this axis, right? Now, the more this angular velocity will increase, what happens is that each of these two atoms, M1 and M2, will actually experience a centrifugal force. So what happens is this one will actually move a little bit here. So difficult to draw with this tool, anyway. Okay, so this one will move a little bit to the right, and this one will move a little bit to the left, because this centrifugal force will try to push them away from the center. Okay, so you notice that the distance between them, if I draw it now with a green line, it's going to become, call it R, which is different from R0. Obviously, R is larger than R0. So, if we move it even faster and faster and faster in rotation, does the molecule split? Meaning, do the two atoms split apart and we break the bond between them? No. So what happens? Why that molecule remains as a molecule? So there is a bond, although actually with the increasing velocity, the angular velocity, the distance between them is increasing and there's a centrifugal force. So let me write that down so that we can understand it. So centrifugal force, okay, call it F centrifugal. So away from the center. But in fact, what makes these two atoms to remain in a bond between them is basically, if you want, a Hooke's law kind of force. So this force here, how I'm going to call it, let me recall the exact name of it. It's the restoring force. Yeah, that's the term. I was missing it. So that's a restoring force. Look, so there is a force here, F restoring. So the more the angular velocity increases, the two atoms try to move apart, but then there is a restoring force that tries to keep them back together. So it's like a spring that has a certain spring constant. So if you want, things happen as the bond is a spring. Things happen as if the bond between atoms, between the atoms in the molecule, is like a spring having a spring constant, call it K, right? And so, since the molecule at the end of the day remains in equilibrium, so let us write that down. Since the excuse me, voilà. Take this away. Since the molecule remains as a molecule, so atoms don't split apart, then there is an equilibrium between these forces, which means that F restoring is going to be equal to F centrifugal. Okay? And it's this relation that will allow us actually to get into more interesting information. So now if we use the non-rigid rotator model, we will be able to get into a new kind of information. So obviously we can still get into the masses if we want of the atoms forming the molecule, that does not change. Now we will be able to get also to R0, which is, if you want, the equilibrium. And you probably now understand what I mean by equilibrium distance, or no centrifugal force distance. We will be able also to get into possibly R, which is that stretched, we call it stretched distance between atoms, and depending on what we have as parameters, we can also get into K. K, which is the spring constant or the force constant of the bond, which is fascinating. So you actually can tell from a study of spectra how, if you want, what is the force constant that keeps the two atoms forming your molecules that you study in place. Okay, so now that we have this quick overview of this non-rigid model, we shall move now to getting into the equations and understand what's going on. Basically, what we just said is written here. So the centrifugal force, which is actually equal to mr omega square, is balanced by the restoring force and kr minus r0, and this actually stems from the fact that basically if you initially have the two atoms m1 and m2 at a distance r0, the one from the other in the molecule, when the molecule starts rotating at omega, and we take into consideration that this is going to move here a little bit and this is going to move here a little bit under the effect of the centrifugal force, well, then the displacement or the elongation, if you want, of the bond between the atoms is actually r minus r0. So Hooke's law tells us the restoring force of a spring, in this case it's the bond is considered like a spring with a certain force constant k, is k r minus r0, or k times elongation. So you put these two equal together, and what we get by rearranging, just you multiply kr minus kr0, and then you take r, you solve for r, and you get r equal kr0 over k minus m omega square. It's just simple algebra. Now, how does that result in a change of the energy, rotational energy of the rotating molecule? Well, basically, if you remember, when we said that the rigid rotator case, the rotational energy was purely kinetic, and that was the kinetic part. So let me perhaps put some, okay, so this was the kinetic part, right? And this was considered the only contribution to the energy when we were taking the case of the pure rotation for the non-rigid rotator, right? So the difference now here is there is another energy, which is a potential energy of the restoring force. So that's a potential energy now that seeks continuously to bring the two atoms back to their equilibrium position when they move away from each other a little bit. Okay, so it's like in the normal spring elastic energy, half kx square. It's just that this x now is r minus r0. Now we need to do a little bit of algebra to just bring things into a nicer way, and you will see why. So what we will do is we will rewrite k r minus r0 squared by considering this, by taking the fact that m omega, sorry, oh, I must eliminate that up. By taking the restoring force, sorry, the centrifugal force, m omega squared, which is equal to k r minus r0. And then you see easily from here that r minus r0 is just m r omega square over k. So r minus r0 is simply m r omega squared over k. And this is what we have plugged in here, right? So r minus r0 squared is m squared omega 4 r squared over k squared. Okay? Now what we have done is we have multiplied the upper part by r squared and the lower part by r squared. Why? Because we wanted to show up I. How? In fact, so let me now remove this. Excuse me. In fact, I is equal to mr squared. mr squared. But here we have m squared r squared. So what we did, this squared is nothing else than this squared, which is going to be m squared r4. m squared r4. So this way we had the m squared, we multiplied by r squared so that we get the r4, so we can write I squared, and then the r squared after multiplied in the numerator, we multiplied it down in the denominator. So now we have I squared and omega squared to have it omega 4. For those who did not see it like this, just write it down and you will find it's extremely easy. So why we did that? So that we can write this part, the new part added by this consideration of the elongation of the bond, similar to I omega squared here, because basically we want to quantify it later. So finally, this gives the energy of the rotating molecule, the total energy. We actually have to introduce the angular momentum P. The reason why we do that is because later on we know that P is quantified in quantum mechanics, and we know how to quantify it. So this means that we could actually quantify this expression of the total energy. Now the thing is, as I said, this is the total energy, and what I need you to be careful of is that there is a mistake, in fact, in this in these slides, okay, on the PDFs, simply because well, I omega squared, if I need to write it in terms of P, I would raise P squared, so this is going to be I squared omega squared, and I have to divide it by I. So here I have put I squared, and this is wrong, okay? So it's P squared, half P squared over I, plus this is also, I mean, it's going to be like you raise it up, so it's at I squared omega 4. You raise this one to 4, this gives you I4 omega 4. So you have to divide by I squared to get it as it is now. And this is the expression of the total energy, and you can verify it yourself on a piece of paper, but in terms of P, the angular momentum. Now in quantum mechanics, this angular momentum is basically quantized as h over 2 pi, so, or h bar, radical j plus 1, with j being the quantum number. So if we implement this expression into the energy, so again here you have to consider this correction that I should make. This is P squared over I. I mean, it's a typo, honestly, but because I have the PDFs and the PowerPoints are with a different version of the Microsoft that I have on my Mac, well, things do not look nice, so I can't change them yet. Okay, so E equal half P squared over I plus P4, half P4 I squared KR squared. We just replace the P's with H over 2 pi. I mean, it's just simple mathematics, okay? So you can just see it, h squared, 2 times 2, it's 4. I mean, let's say 2 squared is 4 times 2, it's 8, so 8 pi squared. Radical, if you put it squared, so it's jj plus 1 over mu r squared, because basically we have got the I, which is mu r squared. And for that one, well, h4 32, it's simple, pi 4, okay. Now we have I squared, so it's mu squared r6 times k. Why r6? Because I squared, it's mu squared r4 times r squared, it's r6 times k, and j squared, j plus 1 squared. Okay, well, I mean, that's not nice to do that mathematics like this, and I'm just trying to guide you if you're trying to do it yourself. Now we go back to this relation that we found at the very beginning when we put into equality the restoring force and the centrifugal force. So R in terms of R0. Why? Because basically we would like to get an expression with R0, because R0 is the equilibrium distance that we basically could tell and know from a previous characterization of the molecule. So again, if you put R in this expression in here and in here, what we will get is this form. Well, it's a bit complicated to explain it plainly like this without doing the calculation, and even more complicated to write all these equations with a digital board without a pad. You can do it yourself, but and verify it, but it has been verified before and it's correct. But do it if you want, just to get in ease with it. Basically, what we get at the end is an expression that contains R0, sorry, instead of R0 to the power 6 instead of R to the power 6. Okay, so easily you can see now that there are two terms. Everything boils down to two terms for the quantified or quantized rotational energy. This term, which looks a lot like the one that we know before, is actually the same. And this term, that's the new one. So this new one basically is the correction on the energy. Okay, this is the correction on the energy that we have to introduce when you take into account the fact that the rotator or the molecule is more real, so there is a centrifugal force and we are distorting or changing the distance. Now you will see that basically this correction is extremely small compared to the actual value of a non-rigid rotator, sorry, of a rigid rotator, which is the first term here. Okay, well, let us see this. I mean, I need to erase all this. Okay, great. Now, here we go. So the quantized expression of the rotational energy in the non-rigid rotator approximation is this. Okay, this is the previous one, and this is the correction that we have to add. Now, remember that at the beginning we just in the first part of this chapter, we said that we deal with this molecular spectroscopy with the spectroscopic terms, and we just introduced a notation where we said that we will actually say that the energy can be expressed as HCFJ, Fj being a spectral term, and just it's in terms of centimeter minus 1, so it's like a wave number. Dimension. It has the dimension of a wave number. So it's just hc that we have to take it out of this expressions to get into fj. So you just do this. You just divide ej by hc, and then you will get the spectral term. So the spectral term for the rotational energy, when we take into consideration the centrifugal distortion, or the centrifugal force, I mean, you just divide all these by hc, and then you notice that here h will go and then c will remain. Here h will go and c will appear. Okay, and now this part is now visibly and clearly the previous fj that we've seen before. It's bj plus 1, and this is obviously our famous b, the spectral constant or the rotation constant. And Now, this here is a new term that we call DC or DCF, so the constant of centrifuge distortion or centrifugal distortion, J squared, J plus 1 squared. Now, obviously, again, here there is a fault. Where is it? Okay. This is J squared. Okay. It's a typo. Nothing called J2. So everything is like when the so things happen as if actually when we take into consideration the non-rigid rotator model, well, then the values that we've calculated before in the rigid rotator will be shifted by a certain value due to this correction. Now let's see how much these values are. Again, let me correct. C square here. And you see, so we write it like this. This is B and this is DCF, and DCF is called the constant of the centrifuge distortion. Okay. Now the thing is, this DCF is much smaller than B, and I mean it's visibly clear, but we can even calculate that. So DCF is around 10 to the power minus 4B. So it's a very slight correction, in fact. Okay, and this very slight correction is just because the effect is very slight. I mean, we are rotating the molecule at energies, but still the displacement of the atom is not huge. Okay, so this is the main message that we need to keep in mind. It's the spectral term, which is obviously in terms of, so you see this is basically in units of centimeter minus 1. So this is a wave number that will show up on the spectrum. And this is the one that we've seen before, and it will be shifted by a certain value. That's all. Let us move on. Now, same thing as before, right? I mean, the lambda or nu bar, this one that I called, if you remember, I called it nu bar spectra. This is the line that will just show up on the spectrum. And if you remember, well, I mean, if you have different level of energies of the molecule, it's only when there is an absorption or say an emission, doesn't matter. It's only when a rotational energy go from one state to the other that this difference shows up on the spectrum as a line, and there's other lines afterwards, right? So this is due to this difference in energy levels. So basically this nu bar spectra is what we see on the spectrum, is the transition in absorption in this case from the levels corresponding to the energies J to the energy J plus 1. So it's Fj plus 1 minus Fj because it's final minus initial. Well, you just need to replace, again I have this typo here. Again, you've got just to replace, to write Fj plus 1, you replace J by J plus 1. Okay. Well, I mean, it's a lot of just simple calculation, simple algebra, but yeah, I mean, I'm not going to write it now. If we were on a board, on the real board, I would have written it, but even that, it's not necessarily interesting. But you just replace J by J plus 1, you put it in here, and you get the Fj plus 1. You remember, here you put Fj plus 1, and then here you put J plus 1, if you want to get Fj plus 1. And Fj, you have it, you do the difference between them, and then we get that the line, the wave number of the line showing up on the spectrum due to the transition of absorption, sorry, is given by this. 2bj plus 1, this is what we have got before, minus the correction, which is 4dcf j plus 1 cube. Okay, so we can estimate that if you do the delta fj over fj, you will get this term, And you notice the following, that this term is very small for actually small j's, and it gets significant a little bit only when j get very high. When j gets high, it means the rotational energy is high. So imagine for j equal 20, so it's really high as a rotational energy. Even at this high energy of rotation, even at this high speed of rotation, if you want, finally, the correction DCF is of the order 10 to the power minus 4 of B. So it's really, really small. It gets to 9% when j equals 30. So when we are dealing with j equal 1, j equal 2, j equal 3, j equal 4, j equal 10, we are below 4%, so it's really unnoticeable. And this is why, for most rotational energies that are not really very high, the approximation of non-rigid rotator is basically correct. Because the correction is extremely small, sometimes even smaller than the spectrometer capacity of resolution to see it. Okay. Now, well, this just shows you, in fact, the values to give you an impression. You see that for low values of rotational energy, the very few values of j's, we are almost the same. It's only when it starts to increase that we can detect a certain difference. Okay, you see, like B here is 10.395, while D is almost 0.0004. Extremely small. Final thing, well, this applies basically not only on the distortion case, but maybe in general, but it's a nice thing to know. We're just going to find a relation between the angular velocity of the rotating molecule and the frequency of the transition. Remember that, and I've been repeating this now more than once, it's redundant, but it's just to make the idea stick in our mind. We just detect a radiation, either in emission or in absorption, when there is a transition from one level to the other. Okay, great. Now we express that as if the energy of rotation of the molecule is expressed in terms of, or manifested in terms of, a radiation. So the energy of it, it's h nu. This nu here is not it's not related to the nu bar per se. It's actually the frequency of the radiation associated to the rotational energy. So that the rotational energy can be written p squared over 2i. Obviously here we're just talking about the rigid rotator case, I mean the first approximation. You just put these two equal together. If you put them equal together, you will find that nu equal e over h and e equal p squared over 2i. This is I squared omega squared 2hi. You basically solve for omega squared and you find that omega squared is 2h nu over I. So this just gives us the angular velocity, because in all the cases before, we just did not use the angular velocity. We did not know how much times per second is actually the molecule rotating. And this is how we calculate it. So omega at the end of the day is going to be, so the angular frequency of the rotating molecule itself is nothing than the square root of 2h nu, and nu being the frequency of the radiation, which happens from a transition over I. So we can tell, in fact, how fast the molecule is turning around itself, which is interesting to my physicist sense, to be honest. Well, now we just do a final example, if you want, of application, and then the chapter is done. This is an example, but that basically also implies a certain knowledge of the course itself, and that's called the isotopic effect. Now, as you know, isotopes are basically the same atom but with a different mass, right? So if we have the same atom with a different mass, what would change in both cases? So let's be more specific. Here I have two gases, okay, CO and CO. However, one of the COs, it has the C12, and the other one has the C13. So what would change between these two molecules? If we call this molecule 1 and this is molecule 2, what would change is obviously the mass. Which mass? The mu. So this will have a mu1 different than mu2. And let's see why. Simply because C13 is a little bit heavier than C12. The oxygen remains the same. Now, this obviously will have an effect on the rotational energy, right? I mean, it's much easier to rotate something that is lighter than compared to rotating something that is heavy. Intuitive, if you want. Okay, so let's see how this can be calculated. And obviously, this will result in slight differences, very small shifts in the absorption lines or emission lines that you observe on the spectrum if we have isotopes. And well, we can see this effect and then study the masses or the effect of the isotope. Okay, let me be more practical. So here we consider the CO molecule where we have two isotopes, as we said. The transition from J equals 0 to J equals 1 happens at, it's given that the transition happens at this centimeter minus 1 and this centimeter minus 1. What does that mean? And here I need you to, this introduces to you the way the questions are going to be asked usually. So here I have a transition. And then I say it happens with centimeter minus 1 and centimeter minus 1. So basically, these centimeter minus 1 and centimeter minus 1, they are the new bar spect that I mentioned before. So this is the line that will show up on the spectrum which comes from a transition. And this obviously is, as you know, it comes from a transition. So it's a new bar of J to J plus 1 if we are in absorption. Okay. So this is something interesting to note. Then when you talk about transition and we give you centimeter minus 1, that's the new bar on the spectrum, which is corresponding to the difference of new bars due to the transition. Okay, let me remove this because it's going to be ugly. Okay. Well, it's just giving us that for the two different isotopes, there is this difference in the lines or the wave numbers that show up on the spectrum between the two cases. We are given the mass, the molar mass of C12 of the oxygen, B of the CO12 case, and B of the CO13 case. So we've got the B's. Now what we want is determine the mass of the isotope C13. That's the question. Now obviously, because we have different new bars here, and we have the different B's, so usually in the case of isotopes, we think about ratios between the different cases of the two atoms. Well, first of all, if we divide the B together, we notice that B is H 8 pi squared mr0 squared over C. Well, you see that what I'm interested in the mass that is getting to change. Everything else remains the same. R0 wouldn't change, C is the same. Only mu will be different between the case where C was 12 and when CO and C was 13. So I'll call this is eta over mu, corresponding to C12 and C13, and if I divide them, I will get that the relation or the ratio between the B of the first case to the B CO13 is nothing else than mu of the CO13 on mu of CO12. So I have the relation between the mu, the reduced mass of the two cases. Now, well, the reduced mass, we know its formula. It's M1, M2 over M1 plus M2. In the CO12 molecule, M1 is MC12. Well, this is also a typo here. I haven't noticed it before. It's without an O here. So that's the mass of the C12 plus mass of O. And here it's mass of the C13 times M of oxygen over mass of C13 plus mass of oxygen. And you divide them. So if we divide them together, you notice that we can actually take this out and this out. And we will get, by multiplication, MC13 this over this and equal to this value. We just do the math. When you do the math, we will get M of C13. I mean, that's a really terrible typo here. I don't know how I missed that, but yes, I did. Okay, it's mass of C. Let me just remove this like this, like this. It's everywhere, actually. No worries. So it's just simple mathematics. It's really, I would say, not silly. It's easy, but yeah, it gets us trained on doing this, because this sort of question, it's usually asked. Okay, so you've got isotope, and we ask you to calculate the mass of the isotope if you want, just simply by this. So you have to think about ratios. Okay. Well, with this, we come up to the end of this video and the end of the chapter. Soon enough, I will be sending you the solution of the exercises of this chapter, and we move to the chapter 3 on the vibration of diatomic molecules. Thank you for watching.